So Rob, is it okay with you if I go ahead and start? Okay. Before we officially start, I wanted to mention to those of you who may have seen Professor Wanda Korn's presentation 2 weeks ago, and especially for those of you who may not have seen it, there's a wonderful write-up in today's Stanford report, well, yesterday's Stanford report on the back. So be sure to check that out. And the talks are posted on the CTL website, although I doubt Wanda's is up quite yet, but I just wanted to let you know that. And I'm Michelle Marinkovich, Associate Vice Provost for Undergraduate Education and Director of CTL, and thank you so much for being here in what is the final presentation in the 2005-06 award-winning Teachers on Teaching. And since it is the last one before we start up again next fall, I'm particularly pleased that Geological and Environmental Sciences Professor Rob Dunbar, who, as I'll explain in a minute, is a member of the CTL extended family, is presenting today on teaching outside the walls. Now, even more than usual, it's difficult with speakers in this series, but especially so today, given how broad Rob's interests are and how amazing his accomplishments are, to try to give a brief introduction that nonetheless does justice. In fact, just to list Rob's major titles, the Victoria P. and Roger V. Sant Director of the Earth Systems Program, the J. Frederick and Elizabeth B. Weintz University Fellow, in undergraduate education, Director of the Stanford University Stable Isotope Lab, Senior Fellow of the Freeman Spogli Institute for International Studies, and Senior Fellow in the Institute for the Environment, takes, as you've just seen, a little bit of time. But let me try to give you some sense of the man as well as the scientist and the teacher. Rob received his BS in geology in 1975 with special honors from the University of Texas, Austin, then went on to complete his PhD in oceanography at the University of California, San Diego in 1981. After teaching at UCSD as a TA, lecturer, and acting assistant professor, Rob then moved to Rice University, where he rose from assistant to full professor. In 1997, to our great good fortune, he was persuaded to come to Stanford. And hopefully this is where he will continue to stay. As somebody studying climate change, marine science, and environmental policy, Rob has chosen to work in fields that are usually not overlapping, Antarctica and the tropics, though in his studies they come together quite powerfully. He is also focused on not just one, but several approaches to paleoclimatology and paleoecology, using chemical, isotopic, and morphological measurements in his research. In spite of the challenge of these multiple literatures and techniques, or perhaps because of them, Rob has amassed a staggering research output. Over 150 publications in such prestigious venues as Nature, Science, the Journal of Geophysical Research, and my favorite, Paleogeography, Paleoclimatology, Paleoecology, known affectionately as Paleo. In support of this work, he has received almost 40 research grants from NSF and NOAA, among others, just since 1994. But Rob is here to talk to us about teaching, and it's a tribute to his commitment to students that on his website, replete with his publications and research grants, as we have seen, He states that, quote, the most meaningful honor, unquote, he has ever received is his J. Frederick and Elizabeth B. Weintz University Fellowship in Undergraduate Education, given in recognition of mentoring and teaching of undergraduates. Just how seriously he takes these responsibilities is very apparent from his website and CV, where his students' publications and achievements rank along with his own. Before I turn things over to Rob, however, I have to mention two last things. His is the only faculty webpage I have uncovered so far that has a picture not just of Rob, but of his beloved golden retriever, Hatch. Personally, I consider a love of dogs right up there with a love of undergraduates, as any of you who know me will have guessed. And as I mentioned in the beginning, Rob is a highly esteemed member of the CTL extended family, since his wife is our own amazing Senior Associate Director for Science and Engineering, Robin Wright Dunbar. About whom we have just learned something new. And now it is my distinct pleasure to welcome to our series Professor Rob Dunbar.
All right, thanks. Thanks, Michelle. And Rebecca, could you kill that white toggle switch behind? Yeah, that's great. Well, thanks everybody for coming. And thanks for that introduction. I guess you might think now that I'm a ringer since Robin and I are married and she works for CTL, but it's kind of funny, there's certain things you can't do with your spouse. Like you should never try to hang wallpaper with your spouse. It's an instant path to divorce, and we actually talk less than you might imagine about the whole pedagogy of teaching. But I have to say, sometimes when I'm really stuck, and I've talked to my grad students, what do I do about kicking this class up and we can't work it out finally, then I'll go to Robin. I should probably turn to her first, right? But whenever I do that, in the extremity of a disaster, impending disaster in a class, she always kind of comes out with something that's totally new, and I give it a shot. And I'll describe a couple of those things here today. It is true. I was greatly honored by that teaching fellowship, in part, I think, because it was such a surprise. I mean, I really do love teaching. I wouldn't be working at a university otherwise. It's right up there with kind of scientific discovery as, the two most important things that motivate me. But that being said, I never would have thought of myself as like an outstanding teacher. I thought I was doing okay with it, and I try to do a good job, but I really was quite surprised by that, and I'm very appreciative of it. It's funny, since I got that fellowship, I've actually started to read articles about how you teach and pay more attention to it so that I'm not found out to be a fraud, Okay, I'm going to walk you through a couple of things here. This is very informal, and there's lots of food over here and sodas, and it's fine with me if you get up move over and grab a cookie or an apple. One of the keys to teaching is food, I've learned over the years that if students are doing something with their mouth, they cannot fall asleep, right? So if people are starting to nod off in class, you can have them chew some gum, talk to each other, kiss, eat something, whatever, but they cannot fall asleep if they're doing something with their mouth. And so go ahead and grab some food if you'd like, and also stop me if something comes up that you want to hear about at the time. Now, this is one of the classes I've been teaching the last few years. In fact, I think it might have been this group that in part nominated me for this award, and this was a class that ran through the fall quarter. We really just had this one field trip. The class was on polar exploration. I think Phil Farrell's son was out with us this time, and we had this overnight field trip, dog sledding, camping in the snow up in the Sierras, and it turned out it was a weekend with one of the worst storms, on record. So we get up here, 40 and 50 knot winds, and some of the smaller students were being blown off to the side. Nobody could see each other. I thought, my God, we're going to lose someone. And I was talking to Gary about this. I mean, field trips are getting a little bit harder to run now in some of the more exotic locations. But the fact is, I brought them all back alive, and they felt so happy about this. That was their final exam, was to survive a night under polar conditions. Okay, this is a shot of my start at teaching in the field. My very first year as a graduate student. My advisor, this man here, took me out on this cruise, and he decided to bring 4 undergraduate students along from UCSD. And he didn't really know exactly what he was going to do with them, but it seemed like a good idea, and so he said, Rob, you're my grad student. You're in charge of these 4 students for 6 weeks. And that was it. No training, no preparation. I couldn't even get him to sit down with me and talk about what they might do. But it worked out. And I showed this picture earlier in the day. Everybody was thinking this must be me over here, but that's actually me right there. And the funny thing is, you know, this is in the tropical ocean, the equatorial Pacific, and I had already cut my hair. This is my tropical haircut. And I used to wear this mule's tooth around my neck to annoy my mother. And it was very effective. Anyway, so I learned a lot of things on that trip, and it kind of launched me into this notion that as often as I could, I wanted to teach in the field. So I'm going to talk about these 3 things: teaching in the field, a little bit about my experiences with involving undergraduates in the research that we do in the lab, and then this is a tough one. I put it at the end because I've been struggling with how to do interdisciplinary teaching for years and years and years and years, and talking to a lot of students about it, and we still don't have the perfect solution to that. So I'm going to end with that in part because I hope that'll spur some comments and discussion. Okay, and I put in this warning here. Last night I was putting slides together, and Robin was looking over my shoulder, and she said, God, it looks like all you guys do is go exotic places and goof around, So this is a warning. What you're going to see in all of these slides, teaching and learning in the field looks like it's just too much fun, right? But the challenge is to keep it fun, really fun, exciting in an adventure sense, and then also pass on the information and kind of ability to think, about learning, to pass all of that on to the students at the same time. So I'll start out with a few tips here. I already went over the food item, right? The food tip. These are some of the things that I think about when I try to structure what I do for work. Teach in the field, close to your subject as often as possible. I know that's easier said for some of us than others, right? Like, I work on environmental issues, so my field is out there. If you're thinking about a Hamiltonian equation, it's a little bit harder. Be selfish, and you have to be a little bit careful about this, because if everybody in a department only chose to teach about what they thought would be most fun to teach, you might leave some important things out. But to the extent that you can, just pick things that are the most fun for you to talk about, and don't feel bad about being selfish in that way, because you will bring this level of energy and enthusiasm to your lectures, to the topics that the students just feed off of. So I think that's a really important thing. I'm a huge fan of engaging undergraduates in my own research projects. Sometimes people come in and they have their own great idea, and I'll either turn them loose or temper it, or say that's a horrible idea, but sometimes they'll proceed anyway. But more often, I'd say about 60% of the time, people come in and just say, I'm really interested in this topic. Do you have anything that I might be able to do? And that's been a rewarding experience 90% of the time. Let's see, the second one, Robin's going to accuse me of throwing this in here for her, But I did start doing this, go for that midterm evaluation and find out what's working and what isn't. And, here's the thing, I always look at my teaching evaluations when they come back in, and I've got some classes now where I've rolled them out here at Stanford 5 or 6 times. Exactly the same class, And sometimes I get all 5s, and then the next year it'll be all 4s, and it's not like I had a fundamentally different approach. What's different is the students. Even with a class as large as, say, 10 or 12 students, 15, every year there's something different, and sometimes they're totally different. And so you walk in thinking, well, this has been a great class. It seems to have worked for people for the last 3 years, and all of a sudden it's not going well. And, this midterm evaluation can help you get back on track. And the quarter is so short that if you get off track, you don't have much time to bail back out, right? So that being said, this quarter I chose not to do a midterm evaluation because the spring quarter is it's like a week shorter than the other ones, right? And it just goes so fast. I mean, you do lose something. You lose one class of content. But I made up for it in part by, we have 6 field trips in the class this quarter, and when I'm in the vans with the students driving down to Monterey Bay, I just ask them kind of one-on-one, but we didn't do a structured midterm evaluation, but I have been doing that more often. Watch other faculty and learn from them. I always have people who I've got my eyes on, you know. I always have had, and I'm sure I always will, people that I look at and I'm just in awe of their ability to explain things. And, you know, Pam Matson, our dean, is one of those people. You listen to her talk about an environmental problem, and all of a sudden, you know, it snaps. And you know, I'll admit it, I steal devices and tricks from her when I learn them. And I talk to other folks. Steve Gorelick in the School of Geological and Environmental Sciences, you know, you wouldn't think that faculty talk about this sort of thing, but we were talking one day at Friday Beer, and you know, I said something like, do you have any favorite tricks that you use in teaching? And he said, oh yeah, I got one, you know. He said, you know how when you explain something really complicated, you're up there at the board with equations, and then you turn it around and you say, are there any questions? And you know, like, the people that aren't getting it at all are going to be the last ones that raise their arms, right? I mean, who wants to admit that? So what he said, he does this thing where he goes, okay, who's with me? Who's got it? You know, and then he raises his hand and he makes all of them raise their hand. And it's the people that don't, you know, those are the ones he'll kind of go after then and work it out with them somehow. But, you know, that's a simple little device, and I never would have thought of that, but I got it from one of my colleagues. And we're at a place with a lot of great teachers. Here's that food thing again. Teach right before lunch, you know. Like, that's what I found. Students, you know, scientific studies show that students are physiologically at a peak right before feeding time. And so teach right before lunch. They will stay awake. Okay, the last one, and this is apropos to the next sets of slides. You know, in the field, you know, the challenge, again, is like imparting some knowledge that it wasn't just a fun trip together. And to set that up, you know, before you go in the field, you need to be very explicit and very specific about what the goals are. And it can't be a very long list, right? You know, people are out in the sun in many cases, but you need to think really hard before you go, what are the goals? And then everything else will kind of follow after that. Okay, remote field work. We do quite a bit of that. In my group, I've taken about maybe 50 to 60 students to Antarctica at this point, a number of students to East Africa, quite a few students on long ocean voyages in the tropics. And it really is the ultimate form of group learning. You know, you're living together, you're together 24 hours a day, you're working together, people are talking about samples, data, analysis, and it is this ultimate form of group learning, and personally I find that the single most rewarding teaching that I do, when that whole thing kind of kicks in and it works really well. So a couple of pros and cons here about teaching in the field. Well, one pro is that there's no internet, right? That's a big distraction. Another pro is that there's intensive contact with students. Obviously, we have direct exposure to the subject matter. There's a lot of peer-to-peer learning, and the faculty aren't too far away. You know, like sometimes when you engage your students in peer-to-peer learning, you give them some topic and say, go off and discuss amongst yourselves, you know, and come back. Sometimes they go off into la-la land, you know. I mean, that can be instructive in itself. They'll figure it out and realize, God, we just made this fundamental error in how to approach this problem. But sometimes they won't figure that out. And the nice thing about a group learning situation in the field is that, you know, the faculty aren't too far away. You can be as unintrusive or as intrusive as you want to kind of monitor progress. You can combine research with teaching, which works great for our students, and then the people that participate generally love it. Now the cons, you know, kind of the same here. No internet, intensive contact with students. You know, sometimes if you're on a small sailboat with the same group of 23 students for 5 weeks, you know, it's maybe a little too intensive. It can be expensive, but we have ways to raise money here at Stanford that people at a lot of other schools do not. This is a big one, you know, I don't know what to do about this. I mean, you know, there's a lot of students here, athletes, people in some of the required class intensive programs like engineering, even our systems to some extent. You know, their schedules are constrained by everything else they're doing, and they really want to do this, and they're the kind of people that would benefit from a field experience, especially a remote one, but they just can't do it. There's limited university-type resources, like we don't have libraries in Antarctica or libraries out on the ship, and sometimes those are pretty useful things when you're turning people loose on a cutting-edge problem. Time-intensive, you know, it really is a big investment of time to set up a trip, to administrate it. You know, if you go out for 10 weeks with a bunch of students and the teaching is one of the big focus points, you don't get a whole lot of other work done unless you do this, you know, combine research and teaching. And then, of course, it's hard to do with some cognates. I mean, I'll be the first to say there are some classes that just must be taught in the classroom, right? But fewer than you might imagine. And we can talk about how to extend, you know, where you can go into the field where you might not imagine that it's possible. Okay, so I've got some video here. I hope it works. I did a preview on this machine last night and it had a few problems. But I'm going to talk about some of the classes where we do day and weekend trips. This is through freshman and sophomore programs. I've been teaching 3 different freshman seminars and sophomore dialogue, sophomore seminars. And the first one is a class that's going on this quarter. I actually filmed these guys this week, you know, 2 days ago on our field trip. Then this one we ran last year. And then I'll spend a little of time talking about these longer trips. They involve smaller numbers of students, but again, over the years, you know, it adds up to larger numbers. Although I should say Stanford at Sea has now had 43 alumni and we'll have another 23 students coming through next year. And again, the challenge for any of these trips, whether they're day trips or month-long trips, is designing the activities, the field activities, so that students acquire both traditional lore and also, you know, learn how to solve problems, learn how to think outside the classroom. So here's the first one. And it emphasizes the point that our local setting here in coastal California, you know, it's perfect for earth environmental problems. We've got the ocean, we've got mountains, we've got tremendous human impacts. You know, there's some really bad impacts that get swept under the rug and nobody wants you to know about them, but you can ferret it out anyway and take the students there. There's, you know, it's a wealthy population, so some really expensive remediation regimes are in play, and you can see how they work here. You know, it's a fantastic place. And I'm not the only one doing this. Our department, Geological and Environmental Sciences, we have all kinds of people working and taking students into the field. Dennis Bird takes students into the Gold Country. We've got these field trips to Death Valley and Owens Valley. We sponsor a lot of students that do field projects, and Ann Egger there helps connect our students with faculty and resources to go into the field. And we've got this sophomore college, which, believe it or not, takes students on horseback up into the Wind River ranges in Wyoming. Last year, Julia Rosen broke her foot. They were so remote, they couldn't get her to a doctor for about 5 days. But she didn't even know it was broken, right? Anyway, so this is a popular mode of teaching and learning within our school. So here's the class that's going on now. In this class, students, the main point is to impart knowledge and ways of thinking about environmental and economic issues that are relevant in the California coast. We have 6 field trips plus regular classes twice a week, and everybody does a project. That's kind of the main structure. And so here we are. This is Tuesday morning, and all of the.
Like going out in the field? Why do you like going out in the field?
It's cold. This is okay.
Everybody.
This trip went out at 5 a.m. right? And each one of these videos has one point I want to drive home, and they're all about 2 to 3 minutes long. This video, the point is, you can run a field trip and still get students back to class at 9 in the morning, right? And they will, and they'll get up for it if it's something exciting. Like, look at this field area. The topic at hand right here is zonation. So this is a place to look at the underlying principles of ecological zonation. And everything in the Rocky Intertidal lives on the surface. So you can see it all. It's all exposed. You go early in the morning in the spring when the tide's low, and everybody had an assignment here to figure out where different life zones started and ended. And it is a little bit, you know, dangerous here.
Not falling down.
And they're very good at responding to commands like that. So look at that thing.
How many arms does it have?
That's a sun star. I hope you guys have all seen a sun star. They can have as many as 40 legs. And this is a way to teach kind of principles of hydraulics, right? These guys run with a hydraulic motor. They don't have regular muscles with muscle fibers. And look at these tube feet.
Oh, he is floppy.
These are scientific terms. They went slimy and gross. Those are the terms, yeah. Now look at her expression there. That was too much, you know. So, you know, that was a 3.5-hour field trip, and they came back energized, and we actually had class later that day, and I gave them kind of the in-classroom part of ecological zonation theory. Okay, the second example is this field trip that we do by dog sledding up in the Sierras. It's a class called Science, History, and Literature of Polar Exploration. I've been teaching that as a freshman seminar, and you know, one of the ideas was to see if we could use this pretty interesting topic to teach some of the principles of physics. And so there is a focus on physics, but it's related to things like how skis work, right? I mean, skis work because there's this overpressure on the edges of crystals that causes pressure melting, which is a physical phenomenon related to the crystallography of ice. How does heat move through snow? Well, you want to know that if you want to figure out avalanche danger. So we go out and we dig snow pits, we measure the temperature, we make some calculations about the thermal regime. We talk about ice crystals. We have a little microscope that we take with us. And we also think about snow and avalanches. So here's this, let's see, I think it'll come on now. Yeah, so there's this class. Freshman seminars, I think, are about 14 or 15 students. It's the perfect size for a trip like this. This guy is a dog sled driver, but he's also a snow and ice physicist educated at Berkeley. You know, he's perfect, and he almost does this trip for us for free because he likes teaching, right? And as Michelle was saying, you know, to do anything with dogs is like unbelievable. To be out there with dogs and undergraduates at the same time. So, but the problem is that, you know, there's always this situation. Oh, I think I somehow stopped it. But I have a solution to this. We're just going to go here where I can control the movie. So one of the problems on a trip like this is, you know, people worry about whether they're capable of skiing, you know, this kind of thing. And we have had a lot of people fall down, but we haven't broken anything. And I try to bring along 2 or 3 competent skiers that they can. And they sleep outside. They dig snow pits, snow caves, right? You know, we can't require this, but everybody goes.
Yeah, Matt was a trooper. Matt was the guy that did the most work helping you with the dog sled.
We're talking about Phil Farrell's son there.
The whole theory behind the snow shelter is that you maintain the temperature of -1 degree centigrade.
And we do that with candles.
Warm, actually, camping is still there.
This to next year's class makes it look too civilized. There is a hut, though, and we cook our meals in the hut, and there's a little chalkboard in there, and we talk about, then the dogs are in there, too. And they're voracious thieves of gloves and socks and things. So then here's class. And in this case, everybody skied up to a slope where there is a potential for avalanche. And we dig a snow pit. And then we spend time in that snow pit measuring the temperature of the snow.
0 degrees centigrade is becoming what's known as isothermal, or becoming wet. And wet snow is a weird beast, and I want to know, having this 0 degrees there worries me a little bit. Oh, I would go -2. Okay, that's good. -2. In the middle of it gives a little knee push.
And then we do kind of a simple mechanics experiment that really is the field test for avalanche.
He's a big boy, too.
Yeah, this guy is 6'9" student. As a freshman.
Whoa!
So there's the avalanche, and then we'll go in there and examine the slip planes and figure out, you know, did it fail where we predicted as a group that it would fail based on our physical measurements. So, okay, let's move on from that one. Oh, that's right, I'm out of PowerPoint. Let's get back into PowerPoint. Okay, so the example with that class was, you know, as I mentioned, I mean, there's some cognates that you just can't teach in the field, but it's amazing how much physics you can teach in that one weekend, right? And even if you can't impart some of the detailed lore of differential equations related to the diffusive flux of heat, you know, they immediately know how they can use, you know, Fick's law to do something that they may be interested in because they're ski aficionados, right? And so that's another challenge, is as much as you can, keep drawing back some of the basic lore that they get in years 1 and 2 of math, physics, chemistry, and biology, and say, this is why this is important. Okay, the third example, and this is an example of something that I can't do very often. I wish I could do. I think it has tremendous value, but it's kind of an extreme case. You know, I've been working in Antarctica for 25 years now, and I go once or twice a year. Every year I've taken a lot of students there, but this was an extreme example. We had a 70-day cruise on a big icebreaker. The PIs that I was with were all either former students or just close friends, and we decided as a group that we were going to take many undergraduates. So we took more undergraduates out, 11 more undergraduates than have ever sailed on this research icebreaker. We only had 3 grad students with us. It's usually, the numbers are usually the other way around. This is on a ship where the ship cost is about $50,000 a day. We had the ship for 70 days, so this is a huge financial investment on the part of the National Science Foundation. You know, our reputation's on the line. We have to publish papers if we want to get funded again. So, you know, it's an interesting experiment to say, we're going to do this. This cruise is going to ride on the backs of undergraduate labor. You know? I mean, we work really hard, too. Everybody works like a dog out there. But we also decided to offer it as a 12-unit class. The cruise spanned the entire winter quarter, and students got back here right before spring quarter started. I took 3 students, and we, you know, since it was a fairly big deal, we invited applications. The students, just to apply, had to take a class in the autumn quarter on Antarctic marine geology. And then I was helped by Julie Kennedy. I think one other person helped me interview the students, and then we selected 3. Then at sea, you know, whenever you go to Antarctica on a ship, it takes a long time to get there. You know, we left from Hobart, Australia, and it takes 9 days to get across the passage to Antarctica. And so we had classes basically all day long every day. And then once they got down there, then each student worked on a project. So here's Melanie Hopkins, one of the GNES undergraduates working at the end of this long core. So here's the movie that goes with this one. And I think this one will play. Yeah, and we'll be all right as long as I keep my finger off the button here. So there's the cruise track. We started in early January in Tasmania, went straight south to Antarctica, and spent many weeks working along the margin. I couldn't get the sound to work on this one, but it's all right. I'll just tell you what's going on here. They still have this tradition in Australia where you know, throw these little these confetti pieces, and then finally they break, and everybody screams and cries. Now this student here, she went with me as an undergraduate in 1979, and she liked it so much that she hired on as a crew member on that ship for 3 years. Now she's a PhD student in Washington. Since you're going into cold country, they make you put on these Gumby suits. They call them Gumby suits. So here are 2 of the students there. And the only problem with teaching class nonstop for 8 days as you cross south is that the ocean doesn't always cooperate, right? And the classroom, unfortunately, on this ship, it does have a classroom, but it's on the upper deck of the ship. And so the students are really good. You know, they'd be in there getting green and run out for a while, you know, throw up, and then come back in. And that's another way, you know, they never fell asleep. So ultimately, you get into the ice, and then the motion changes. It's not this rolling motion that makes you toss your cookies. It's more of a bump and grind as the ship makes its way through the ice. But we had 2 students working on the ice. See all this brown stuff in the ice? Those are plant and bacteria communities that live in the ice. And in one sense, it's the single largest continuous sunlit ecosystem on Earth, and we know almost nothing about it. So, you know, there's so many fundamental problems. It's easy to give an undergraduate a problem that's going to get them a paper out at the end. Lots of ice. You know, whenever you're in rough weather and the temperatures are 10 or 20 degrees below zero, all the equipment we work with is, and we actually had not only 11 undergraduates, we had, I think, 27 women on this cruise. So that was also a record. So when you see photos like that of, you know, people breaking ice off of the equipment and it looks like it's all women doing the work, well, that's because, you know, on any given shift, that was 3/4 of the people available to do the work. Not immediately, but after 2 or 3 weeks of training, students do get involved in using some of the heavy equipment, and by the end of the cruise, people are operating winches. They're doing things that, you know, normally you wouldn't think our students would be doing, but it's done safely. There's a lot of emphasis given to safe work practices outside. Here's one of the main tools that was used by our students. It's a piston core, 110 feet long. It gets dropped into the mud, and you recover this archive. It's like a book, and you read each one of the pages as you work your way down the core. So these are all undergrads here. These are the cores that come up in 10-foot sections. Students, we had some postdocs and grad students along as well, but mostly undergraduates would be sampling these things, and they'd actually get some of the mud, you know, in their hands on the ship. We do all the chemical things that we do. The ship has superb laboratories. We also collect a lot of water. This is a very complex device that's attached to a wire, and it goes up and down in the deep Antarctic water column, and it collects very accurate measurements of the physics of the water. And then each one of these 24 tubes here is a bottle that can snap shut and collect a discrete water sample. So we had 2 of our students working on these water samples and learning something new about the way the Southern Ocean works. You know, it's an icebreaker, so this has this huge door in the hull amidship so that the ship can deploy this kind of thing safely in rough weather. And of course, lots of icebergs. What we would typically do for kind of taking a break, because you work 7 days a week, everybody works 14 hours a day, 7 days a week, 10 weeks in a row. You know, that's just how it is. There are no days off, but you might spend an hour kind of cruising through a field of icebergs like this. And this was one of the most common tools. It's another coring device that the students use. This one was particularly useful for student research because we do all the sampling and observations in real time on the ship. So these are all undergraduates here carrying this sediment core in that's been recently recovered. Comes into the lab, and people are on shift work, normally 12 hours on, 12 hours off, but there's often, you know, you'll work a couple of hours into the next shift to help out. And the amazing thing is, I mean, nobody gets burned out on that. Easy for me to say, right? Maybe they did and they didn't tell me, but my impression is that people do not get burned out. They're just so excited. You get to see, you know, the history of sedimentation, the history of climate in Antarctica. So this is obviously time-lapse. This is like a 12-hour sequence where the camera is recording a frame every few seconds, and it shows the kinds of things that are done to these sediment cores. We do physical properties. We measure seismic velocities. We collect samples for pore water chemistry. We sample the cores for diatoms and look at them under the microscope. And the ship has an array of laboratories that is set up to let you, you know, figure this stuff out. And then at the end of the cruise, you know, we've got another 10 days to go back to Africa, and people show their results. And the undergraduates all had to write up a little paper before this trip even ended, right? So I think we can probably terminate this now, but here's a really long core on this bench and one over here, and altogether there's about 25 people engaged in working on these things. They call it butchering the core, is the scientific term. Okay, did it work? You know, in my assessment, I think overall NSF gave us kudos for this. At this point, we have about, you know, and what the National Science Foundation cares about first and foremost is research productivity. They do have this element of outreach and education that has kind of risen to prominence. Many of the people in the room here know about that. But still, when it comes to getting that next grant funded, you know, that's about 10% of what they look at. 90% of what they look at is your research productivity. So we've published at this point about 12 peer-reviewed papers. There's another 8 or 9 in the pipeline, which is about right for a cruise of that length. Of those 10 that are out already in the peer-reviewed literature, about 7 of them have undergraduate authors, and 4 of them have undergraduate first authors, right? And we do make hay with that. I mean, we point that out to NSF, and we send these students to NSF to talk about their work. And our feeling is that, you know, maybe if we had gone entirely with grad students and postdocs, that we would have had a few more papers out faster. I mean, that's true. You know, we really would have. But our feeling is that NSF will appreciate that we did this experiment and that results showed that we can involve undergraduates in research as part of the learning process. And certainly, you know, all of the 11 students that were out there, I think 9 of them are in PhD programs at top universities around the nation, and I think this was transformative for them in their undergraduate careers. Okay, so that leads into what I think about undergraduate research projects. Well, they're always, well, almost rewarding, you know. I mean, I've had a few duds, and if a dud occurs, it's usually that you feel like, as a faculty member, you know, God, this person was so great, and they worked so hard, and I worked my butt off to help them, you know, come to a successful conclusion. And then they and they did, you know, and then they disappeared. You know, they got onto something new, and they weren't able to take that final step to write things up. And you know, that is discouraging, but on the other hand, there's mechanisms to deal with it. You can give people like, okay, you got 6 months to write it up, you know, otherwise I'm gonna write it up, and hopefully you have the time to do it, and they go from first to second author. You know, there's mechanisms you can put in play, but it does hurt sometimes if you've really put a huge amount of effort in. And you know, the thing is, I mean, our undergraduates have so many things going on in their lives, you know, they don't have a set profession yet, so it's kind of understandable, right? They're gonna flip from one thing to another. It's a great way to teach analytical thinking, you know. Here's a data set, interpret it. I mean, it doesn't get any better than that in terms of just compelling somebody to think about how to answer a question. Sometimes they publish, although, you know, to be honest, the publication rate's probably about half that of grad students in the same setting, you know, which is, I guess, about what I expected going into it. But when they do, it's very rewarding. This is key, you know, here at Stanford, you know, the Campaign for Undergraduate Education and some other vehicles have brought in a huge amount of money. You know, our undergraduate students have access to research grants. They can get that money directly from the vice provost. How nice when a student comes to you and says, I want to work in your lab this summer, and I already have my funding for it, so you don't have to find any money for me. You know, like, oh, God, that's fantastic. Sometimes their writing is superb, and sometimes it's awful, you know. And the thing is, if you put a lot of time and effort into the project and their writing's awful, you got to help them. You got to help them with it. I mean, that's just a commitment you got to decide to make from the beginning so that you get the results out there. And then the last thing, you know, what I've been trying, and I don't think I was very good at this even 6 or 7 years ago. You know, I'd kind of have my own lab group of grad students and staff, and then my undergraduates that I worked with over here. But I kind of came to realize that, you know, they were missing out on a lot by not being fully integrated into the lab group. And also, you know, a lot of my grad students are at least as interested as I am in teaching. You know, they love spending time with students and helping them understand things, and I was not making those folks available to the undergraduates. So now they come to our lab meetings, they come to parties at the house, you know, and in many cases, I think they actually, at the end of the day, they've spent much more time with my grad students than they have with me, right? But it just works out that way. So I think that's a great way for integrating undergrads into your research program. Then choose your students carefully. You know, here's Dave Monroe, Alice Cook. They were applying to go on a long Antarctic cruise in 1998, so before that 10-week one. And you know, you spend a lot of time out in the field with these folks, so you want to, you know, make sure they're truly interested in, that they have some resiliency to the trials and tribulations of life at sea. Here's Dave Monroe, a couple of weeks later, working out on the sea ice, you know, where it's extremely cold where we were that particular year. Sometimes we're camping, like imagine 4 people camping together in Antarctica for 6 weeks, you know. Like you can't get away from other people, right? You got to choose your students carefully. I mean, to illustrate the challenges, that's our toilet seat, right? So, I mean, imagine, you know, there's no bushes or trees. There's no topography. It's sea ice. You know, we're camping on the sea ice, and every time somebody wants to use the toilet, well, you know, think about it. It's an interesting setting. And it never gets dark. It's light 24 hours a day. So, despite this, you know, students love to go, and I like to be there with them. And here's just 3 examples of papers. Fedi Arahina is a GNES, was an undergrad when she came out with us, and she wrote this as a reviewed paper on, she did a project on using seismic data to connect between boreholes that had been drilled. And last night when I was putting this slide together, I actually looked it up under the citation index, and she's got like 40 citations on this paper that she produced as an undergraduate. I mean, that's pretty cool. You know, she contributed something very useful to the literature. This paper we're having a few problems with, but I know it's going to go this time. Charlotte Stevenson was out with us, Stanford at Sea in 2003, Lori Katz 2 years later, And we went to the same place 1 year and then 2 years later, and they collected the same kind of data sets, right, on fish. And Jill Bible was part of this project too, right? So, are you still an author on this paper?
Not really.
Not really?
My coral stuff didn't really.
Oh, okay. Well, the paper, as I said, you know, this paper has morphed many times, and we sent it to Science, we sent it to Nature, we sent it to Marine Ecology Progress Series, and we always get these reviews back saying, man, what a really interesting data set, but you should have done this many more analyses, or you need to go back in the field, you know. And the problem is, if it's an undergraduate-driven research project, it's seldom that you have the opportunity to like go back and redo the experiment, right? You get that one shot. But we've tuned it up yet again, and I guess the point here is that the first two authors, you know, were undergraduate students at the time this work was done, right? And I mean, the author list has kind of changed. It's a little bit shorter now than it used to be as we respond to the reviewer comments and we try to get this thing out. But it's off to coral reefs now. And then Guy Marion, who's here, he was a Goldman Honors student at Stanford, and as an undergraduate, he wrote a proposal, got some funding from VPUE to study how coral colonies that are growing in Bali in Indonesia record the runoff from the islands, basically human-induced pollution of the coastal ocean. And he got this paper out in a peer-reviewed paper in Marine Pollution Bulletin, and I know that's opened up a number of doors for him. He's a student in Australia right now, but he's actually visiting Stanford for a couple of months doing some more analyses. So, you know, that's 3 examples. I could show you another 6 or 7, I guess, that I have personal knowledge of. But the point is this, you know, if you involve your undergraduates in your research program, scientific research program, it will come to pass that they take the lead as authors on papers that you feel very proud of. And that is quite rewarding, and I think we see a lot of that happening at Stanford now. Okay, the last thing I wanted to talk about was Stanford at Sea. This is a collaborative program that we do with Sea Education Association, and it's myself, Barb Block, Theo McKelly, down at Hopkins Marine Station. We teach a class that takes us to Hopkins Marine Station for about 5 weeks, and then we go to sea on a big sailboat, 140-foot sailboat. So 1 sailboat, 24 students, 3 faculty, 3 TAs, 1 cook, and 7 professional crew. That's actually a small number, and what it means is before we're allowed to leave the dock, right, these students have to become part of the crew in the eyes of the U.S. Coast Guard. They have to be trained up on line handling and this sort of thing, and they do. By the time we're done with 5 weeks at sea, you know, the students navigate, they call out the sail handling orders, they do everything. They set the mission. And so this is a particularly exciting class. We can offer it to, you know, 23 or 24 students every year. Again, 5 weeks at Hopkins Marine Station, 5 weeks of sail training and scientific research at sea. And this one, I was never able to get this one to just run on its own, so we're going to run back over here. This is my last video. So we start in Hawaii. We don't always have to start there. I'm trying to take this ship to Antarctica, and I'm running into some resistance from the insurance company that insures this boat, but I'm working on them. So this is in Hawaii. The students are, you know, immediately as you're leaving port, students are at the helm. They're handling the sails. They're pulling up all the lines. So here are our undergraduates hauling in some of the mooring lines. This guy is the chief mate. And there's usually 3 or 4 very experienced sailors. You know, this program has an excellent safety record. So here we are going out of Hawaii. It's a congested port area. So we're going out mostly under motor, but, you know, even though it's congested, there's a student at the helm from day one. In fact, there's almost never a time when a student is not steering this large sailing vessel. So here are the sails going up when we've immediately left the harbor of Honolulu. And you can see the boat starting to move. This is kind of the only unfortunate aspect of the trip is that, you know, people don't think about it, but Hawaii sits in some very rough ocean. And you go from the harbor where it's flat calm out into 15 and 20-foot seas like that. And the first time we taught this class, we lost 30 people to seasickness right away. And it wasn't just our students. We lost the second mate and the third mate as well. But, you know, we just tie them onto the rail. make sure they don't go overboard. And so here's people handling the lines. You know, there's very little in the way of modern kind of electric motors that help sail the ship. You know, it's done with arm sweat and a few mechanical advantages. So students go, they yell out, laying on, when they're going out onto the bowsprit area, because there's a whole series of sails out there that we use and operate. This sailing boat can go 12 to 13 knots under kind of moderate wind conditions. And there's a lot of rope handling. That's what drove me crazy, you know. Like, I get yelled at too. I got yelled at a lot for doing the wrong thing with the rope. They have to learn, like, the names of 59 lines on the boat. And I still don't know all the lines on the boat. Here's that same kind of instrument. You know, the National Science Foundation outfitted this boat with $2 million worth of modern oceanographic sampling equipment. And so every student has a project that they're working on, a science project. And so there might be 2 or 3 students that are dependent upon water samples that come up. They take that water and make microscope slides and count plankton. There's this whole process. Maybe once or twice a day we would launch this thing. Barb Block was calibrating her satellite tags. We'd calibrate them on this thing for temperature and salinity and light, and then she'd implant them in tuna, and we'd track those tuna for the next 2 months. So here's one of the things that we do. You know, you do have to be creative about finding the fairly simple analytical work that can be done out at sea. You know, if we had access to a really big lab, we'd do more things, but it's a tight space there on the ship. We climb, we go aloft. You don't actually have to go up there to do much sail handling, but it is a popular place to be. So there's Seth Bushinsky, and Logan is one of our program TAs in Earth Systems next year. And one of the exciting things about this is going to foreign countries, right? So this past year we went to the Republic of Kiribati. I'm sure you've all heard of Kiribati, the largest nation on Earth, right? 7,000 kilometers long, 85,000 people. But we go there, and a lot of the students end up working in the ocean. Let me turn that down a little bit. I'd say about 2/3 of the students, I shouldn't say ocean, I mean everybody's doing something that's marine oriented, but a lot of the students end up working on coral reefs, and they'll do projects on the chemistry or the biology, the ecology of a coral reef setting. And these islands, it's just, you know, a paradise for comparative ecology. You know, you go from these islands that have never had a human being living on them. There's no historical evidence. And then islands that are fairly heavily impacted. So we've done some of that work. This student designed his own project. He's an engineering major, David Goodeye, and he wanted to measure the strength of corals. And so here he is with his... Can you guys hear that? Okay. And is this a special engineering device?
This is not a special engineering device. It's just a crazy engineering device.
But see, it's perfect. You know, it's so simple. I mean, he would set these things, you know, and keep filling up this bucket with water until there was enough tension, you know, enough stress on it to snap it. And he's able to publish this kind of fundamental strength data on corals, which relates to why you find certain corals where there's big waves and other corals where there's small waves, right? So Karen here is catching squid for a student that did PCR work to do genetics, DNA work, and they discovered a new species of squid. Like normally when you discover a new species, it's some tiny thing, insect of the sea, but this is a big squid. They navigate with sextants. That's a gold mine for geometry and kind of astronomical considerations. Everybody learns how to cook if they don't know how to learn or don't know how to cook already, which is actually most of them. The food's very good, and 2 to 3 students are working in the galley at all times. Barb, Theo, and I do some cooking as well. There's a little laboratory or a computer lab here with modern equipment. He's one of the mates that's grading some exams. So this is class at sea. We'll watch this just a little bit. See, at this point, everybody is doing fine with seasickness. I like this t-shirt here. Can you see what it says? Strive for grooviness.
In the last 24 hours, we've done a lot of science. We've had 3 hours and 19 minutes of science station, and that's include carousels.
Is it making you seasick?
Digging and nuisance hose. Anyway, a couple things that you might have noticed is that in the last few days, we've had a dramatic increase in frequency and intensity of squall, which, if you would have noticed, I have mentioned that over the last.
So everybody gets an assignment, things to talk about.
I'm thinking that's probably because we are getting closer to the IPCC, where there is increased evaporation and intense precipitation. Over the last 24 hours, we've had 5 surface stations.
Creature features.
Carbon and chlorophyll plus our daily hydro test. We did a Newston net, which was nearly 100% hyperic amphipods, and I quote Barb in saying, I wonder what it tastes like.
Now, Barb Block eats everything that comes up.
Species have different patterns of photophores. So, you get a chance, you can look at one of the mitochondria we pick up, and you can look at the scope to see little bluish lights. And
It's making me kind of seasick.
And they give
So
us
at this point, it starts to rain.
most animals that have these.
So we moved inside.
Other documented cases of barracuda attacks have been actually from full aggression by humans trying to spear them. So go ahead and try to spear your barracuda. And Corey, what do you do?
So we do role playing, you know, the kind of stuff Wanda Corn was talking about. And this is an amazing exercise. M&Ms dropped into the ocean, and you count how many seconds it takes to where you can't see them anymore. It's light extinction as a function of color. It's pure physics, right? And it works great. The ship has all this fancy gear. There's our ship track. We measure temperature and salinity. There's a huge amount of underway data that's collected, and some folks do their projects on that. But again, there tends to be a focus on the coral reef systems that we visit, and we go to some places where you can see biodiversity that's really unusual, hard to see anywhere else in the Pacific Basin. And lots of sharks too, actually. So Palmyra Atoll is one of the sharkiest places around, but there's so many other fish that you really don't have to worry about it. Like, the hard thing was to keep students from chasing the sharks, you know, to take pictures of them. Okay, that's the last video, and I've got a couple of more minutes here, and then we will end. And I wanted to just say a little bit about interdisciplinary learning. I've just got, I think, 3 slides on this. And I guess make the point that, you know, I mean, one of the ways that I know we can engage our students is this issue of kind of knowledge that's useful, right? And the point is that many of the most pressing problems that face humanity today do involve the Earth. Not all of them, but many of them do, and its resources. And it's pretty easy to demonstrate that these problems are best approached with some kind of interdisciplinary knowledge base. And you know, that was the whole premise of the development of the IPER program here in this school. That's the Interdisciplinary Graduate Program in Environment and Resources is, you know, can we somehow create new knowledge or teach people to how to create new knowledge that helps address some of these problems, clean water, energy, climate change, you know, volcanic hazards, land use change. And it's so easy to see, you know, that like we know the solution to climate change, right? I mean, man-induced, we just stop burning fossil fuels, right, and keep the CO2 level under control. But, you know, that's the easy part of the problem. The hard part is, well, what do you replace fuels with? What are the economics? How do you engender, how do you promote a transition that's actually going to work? And to answer those questions, you need to know a lot about other topics beyond science and engineering. And so one of the things I would say, I won't spend much time on this now, but you know, when I first got here and started hanging out with Steven Schneider, he was always drawing this distinction between interdisciplinary and multidisciplinary. It used to drive me nuts, you know, but over about a year and a half, I came to realize, you know, the point is so important and it's so apropos for understanding the nature of the problem. And that is, you know, interdisciplinary is taking material from many disciplines and actually using it together in a highly integrated sense. Multidisciplinary is being aware of the disciplines and maybe taking a little bit here, a little bit there, presenting them, but not integrating them. And we're still doing mostly multidisciplinary teaching, right? We've made some progress, but not as much as we'd like to make in interdisciplinarity. But in the earth sciences, I mean, this is an interdisciplinary playground. We've got the Earth Systems Program, we've got IPER, we've got environmental issues. In all over Stanford, I would say, there's a small student-to-faculty ratio, which makes this kind of learning and teaching much more straightforward. We train our students, because of this low ratio, we can train our students in research as well as cognates, and often to answer a research question, you're confronted with this interdisciplinary gulf. You can't get to the answer without learning something new in a different field. We do put our students out in the field, but how do we prepare them to be interdisciplinary problem solvers? And this is where I'm still uncertain about the best way to go. But one of the things that we've been trying, and I've certainly been trying, is teaching via a case study approach. You know, hindsight is often so useful. You know, when people as a community, a society, a legal system, a regulatory system, when they're faced with an environmental question or a challenge, you know, they start, you know, reaching out for straws, and they put in place practices, changes. Scientists come in and collect data, you know, and you never come up with the right solution initially, but over time, you know, scientific process, you figure out what worked, what didn't work, and it takes many years. Of course, you don't have many years to teach this stuff, so just doing that case study approach, just going back and focusing on, you know, how did the puzzle come together through time, I've found to be maybe the most straightforward way to illustrate some of these interdisciplinary principles. Then you can design group activities that encourage students to discover for themselves, because if they don't figure it out for themselves, they're not really going to understand, you know. If you tell them this is what was missing and this is why it didn't work, yeah, that's, you know, they've learned about that one case, but they won't have an appreciation about how to take it further. The specific case is a lot less important than what can be learned about knowledge integration. So it's great to have something that's really exciting, but you know, we try not to get too focused on picking out specific cases. And then the last thing is something I think I've learned from our TAs in the Earth Systems program. You know, we have this thing called ES10. It's the Introduction to Earth Systems, and you know, the idea is to bring some of the best teachers on campus together to teach about the Earth as a system. And they really are good teachers, but there's a lot of them. You know, there might be 10 or 14 students. And how do you herd this group of, you know, sometimes cantankerous, you know, always independently minded faculty? How do you get them to integrate with each other so that the students feel like they've got this package being delivered to them, you know, where every faculty knows what the other one's talked about? And it's hard to get the faculty to do that, but the TAs can. And we, you know, over the years, we've had the TAs redesign the class. The TAs go out and talk to the faculty and show one faculty member what the other faculty's talked about. They say what they think worked, what didn't, and the people pay attention in it. And it's made such a difference in the value of that class. And I think it's one of the reasons that this year we had record numbers, you know, 150 students in that class. So that, I think, is extremely important. And you know, bring them in as early as you can. You know, get your TAs assigned half a quarter before you roll out of class, and start meeting with them and ask them how they would teach it. You know, and I learned stuff from my students that I work with as TAs. So here's the ending. Where would you rather teach? Here? This is the class I was just teaching in at 11 o'clock this morning. Or here? Look at happy, smiling faces. And you know, I think many of you know we have sophomore college, we have freshman and sophomore programs, we have money available from VPUE, some of which came from the Campaign for Undergraduate Education, and we have Stanford's culture where, you know, the walls are low between departments and schools. And for me, you know, this is a place that promotes and favors interdisciplinary learning, you know, as a big group, more than any other university I know about. So it's one of the things I value about Stanford. And I will stop there. Thank you very much for listening.
I think we will have to stop here. But thank you all so much for coming today. Thank you, Rod, for just a wonderful, wonderful presentation. And we hope to see you in this series next year. Thanks again.
Thanks. Yeah, I'm sorry. That's my fault. I didn't leave time for questions. But if anybody wants to talk about some of this stuff, I'm available. So.